What's up, y'all? I'm Mindful, back with part 3 of the Paradox and Thought Experiment Iceberg. This is the last and final part of this series. If you haven't seen parts 1 and 2, go check that out. I'm going to leave the link to those in the description. I hope y'all guys have enjoyed this so far. I've had a blast making it. If y'all haven't liked and subbed by this point, and you've watched the other 2 parts, I would appreciate it. You don't have to, but anyways, we're going to jump right into it and get this done, so let's get into it. Alright, so the first entry on tier 5 is technically one I left out in my last video, and this is the Faraday's Paradox. This one had like one of 2 that you could possibly mention. One was with chemicals and the passivity of it, and this one is more of like electrochemistry and stuff like that. So this one refers to a situation in electromagnetism where a time-varying magnetic field fails to induce an EMF or an electromotive force in a closed loop, even though the magnetic flux through the loop is changing. So this appears to contradict Faraday's law of electromagnetic induction, which states that a changing magnetic field always induces an EMF in a nearby conductor. So this paradox is resolved when you consider the complete circuit and take into account the electric field, which is induced within the conductor itself. This internal electric field opposes the change in magnetic flux and affects the distribution of changes in the conductor. It's worth noting that this isn't a true paradox, but rather a nuanced aspect of electromagnetic induction that requires a more detailed understanding of the underlying principles. So the first actual entry on this tier is the Bertrand's paradox, which is a problem involving circles and chords. So imagine a circle and you want to randomly pick a chord, which is a straight line connecting 2 points inside the circle. Now say you want this chord to be longer than a side of an equilateral triangle inscribed in the circle. The probability of this happening depends on how randomly you choose the chord. There are different ways to choose this chord randomly, and each way gives a different probability. It's a bit like saying, let's pick a chord randomly, but there are different ways to define randomly, and each way gives a different chance. So the paradox in this isn't actually just like a mind-blowing contradictory paradox, but it's actually a paradox on why you should state the rules of something so clearly, because the definition of the word randomly is not always very clear and can lead to different outcomes. The next entry is Friedman's paradox, and for this one, imagine you are trying to build a statistical model to predict something, which is a dependent variable, based on various factors, which are predictor variables. So this one does have a lot of math in it that is very complicated, so I'm going to put it in simple terms and just basically tell you that if you have a situation in which there is a lot of predictor variables compared to the amount of data you have, statistical tests might wrongly suggest that certain factors are significant when they are not. This happens more frequently as the ratio of predictor variables to data points increases. So Thomson's lamp is an infinity paradox that goes as follows. Consider a lamp with a toggle switch. Flicking the switch once turns the lamp on, and another flick turns the lamp off. Now suppose that a being is able to perform the following task. The being starts a timer, he turns the lamp on, at the end of a minute he will turn the lamp off, at the end of a half a minute he turns the lamp on again, at the end of a quarter of a minute he turns the lamp off again, so on to infinity, and at the end of 2 minutes he will have performed an infinite number of tasks. So is the lamp on or is the lamp off? So the creator of this, Thomson, stated that it seems impossible to answer this question because it cannot be on, because that being would have never turned it on at once without ever turning it off, and also it cannot be off because it would have had to have been turned on in the first place. So therefore the lamp is both on and off and a contradiction. So the next is Gibbs Paradox, and this is a puzzle in physics that arises when thinking about the situations of identical particles when they are mixed together. So according to classical ideas, if you mix 2 identical gases, the disorder of randomness, which is entropy, should increase, but it turns out that the classic view doesn't actually match reality. Now, to solve the paradox, you take into account quantum mechanics, in which electrons and atoms, very small particles, are mostly indistinguishable from each other. This tells us that identical particles follow different rules depending on their types. Bosons or fermions, I don't really know what either of those means, that's just what it said, but their behavior is not exactly what classical physics can predict. So the resolution involves understanding the quantum nature of particles and how they interact when most are truly identical. The next entry is the potato paradox, and the potato paradox is the simple problem that goes like this. Suppose Fred brings home 100 kilograms of potatoes, each consisting of 99% water. He then leaves them outside to dry so that way they consist of 98% water. What is their new weight? You would probably think that since they only lose like 1% of their mass, it would probably weigh something like 99 or 98 kilograms, but it actually weighs 50. The reasoning behind this is because originally potatoes consist of 1% dry mass, and therefore in order for the potatoes to have 98% of mass of water, they must have 2% of dry mass. That means the dry mass should have doubled, and therefore the weight of the potatoes would be halved. Again, there's a lot of complex math to this, but that's just the simple way that you should hopefully be able to understand. So the next paradox is the Edgeworth Paradox, and this is one that hasn't been seen on this iceberg yet. This is an economics problem, which comes from the phrase constant returns to scale. If you're not an economist, this means that doubling the inputs, like labor, capital, land, or entrepreneurship, leads to a proportional increase in input. If you don't know what this means, like you're not an economist, this means that doubling the input, like land, labor, capital, entrepreneurship, all of that should lead to a proportional increase in output. However, when dealing with international trade, this does not always hold. For example, if two countries have constant returns to scale, then it could be assumed that the terms of the trade should both benefit both countries. Now, even though both countries have constant returns to scale, the terms of the trade will move against one country, making it worse off for the other country. Again, this seems counterintuitive because assuming that both are under constant returns, both countries should benefit from the trade, however, both don't. So the next is Curry's paradox, and this is another linguistic paradox that revolves around a sentence that claims something like, if this sentence is true, then A. For example, if this sentence is true, then Germany borders China. If you assume that this sentence is false, then you are assuming that this sentence itself is contradicting and basically wrong. Basically, it says that you must first deduce that the first part of the sentence, this sentence is true, and then from that, you can deduce that the second part of the sentence is also true, but it's actually wrong. So, paradox. Alright, so the next entry is Supple's paradox, and this is a kind of confusing physics one, so I'm going to try my best here. So, imagine you are a submarine at rest in water, neither sinking nor floating, you are perfectly balanced. Now, assume that this submarine speeds up to the speed of light, and then something weird happens. Let's also say that there are observers that can see the submarine, even though, I would assume you'd be in the middle ocean, but let's just say that there are observers that can watch you. These people watching you would think that the submarine is sinking due to the high speed that it's going at. However, you being inside the submarine, you would think that the water is getting denser because of the speed, making you believe that the submarine is going to float. So again, here the paradox is actually from the point of view of which you look at it, and that there's actually no paradox at all. It's just how you are looking at the situation. So the next entry is the Einstein-Podolsky-Rosen paradox. Forgive me if I butchered that, but this is a quantum mechanics one where basically Einstein states that he believes what we know about quantum mechanics was incomplete. If you've watched the other videos, then I've talked about particle entanglement quite a lot, so you should know what it is. But for the people who haven't, particle entanglement is a concept where you measure the properties of one particle, and therefore you should be able to know the properties of the particle that it is entangled with. Anyway, the paradox is when you measure one particle, and it seems as if the information of the second particle is traveling faster than the speed of light, which should be impossible. The simple explanation to this is that some things can never be explained by the principles of quantum mechanics and, stuff we base our world off of, and basically there's always going to be something unknown, hence the uncertainty principle in quantum mechanics. So the next is Loschmidt's paradox. Again, sorry if I butchered that. But anyway, this paradox states that it should not be possible to predict a situation's past based on an irreversible process. So this theory is based on the second law of thermodynamics, which I've talked about quite a lot in my other videos. But for those of y'all who don't know, this is where everything's temperature in the universe will eventually balance out. It's very simple terms, but that's basically what it is. Anyways, this paradox states that suppose you have an arrow of time. As time moves forward, using entropy, things tend to get more messy and disordered, making things more unpredictable. However, the laws of physics tells us this law works the same forwards and backwards. However, if you use the laws of physics, you should know that this law should theoretically work the same forwards and backwards. But at the same time, we are progressively going towards more disorder and coming from more order. So there have been many solutions to this, but the one that is most popular is a statistics answer that says that while things are physically reversible, whenever you have a lot of particles and small things moving around all at one time, things can tend to get messy very quickly. So that's what it is. So the next paradox is Hardy's paradox, and this involves the idea that a particle and its antiparticle can interact without annihilating each other. So experiments have been done on this and prove that this can happen, which they use polarized photons for. But basically they suggest that past events can be inferred after their occurrence as a probabilistic wave collapse. In other words, there cannot be a theory assuming that the system's state of reality are independent reactions as a result of measuring apparatuses. So the next one is the Planck of Carneades, I don't know, forgive me if I butchered that, I definitely did. But this is an ethics thought experiment dealing with two shipwrecked sailors. So suppose that there are two shipwrecked sailors, Sailor A and Sailor B. And they're both in the middle of an ocean, and there's a plank in between them that can only fit one of them, and the other one will drown. Sailor A gets the plank first, and Sailor B subsequently pushes off Sailor A, causing Sailor A to drown. Sailor B is then rescued, and the thought experiment wonders whether Sailor B could be tried for murder. But since Sailor B would drown if Sailor A were to stay on the plank, couldn't this considered... But since Sailor B would have drowned if Sailor A had stayed on the plank, this could be considered an act of self-defense, even if Sailor A wasn't doing anything directly to harm Sailor B. So the last entry in Tier 5 is Gödel's incompleteness theorems. And these are two theorems in mathematics that basically conclude that there will always be a type of incompleteness to math. This theorem states that in any formal mathematics system that is expressive enough to include basic arithmetic, there are true mathematical properties that cannot be proven within the system itself. Basically, there are things about numbers that you cannot prove with numbers alone. The second theorem, in simple terms, basically states that if you have a mathematical system, it can't prove that it itself won't give you something wrong or any contradictory answers. These theorems don't prove that math is completely flawed, but however does prove that math itself has its own limitations, where something else would be required to prove the validity of it. The first entry of the last tier, Tier 6 on this iceberg, is the prisoner's problem. You guys might have heard this one before, but it's still interesting nonetheless. But basically, in this situation, you have 100 death row inmates who have been given a chance of freedom. Each prisoner is labeled 1 through 100, and the warden has put all of their numbers in 100 boxes that are also labeled 1 through 100. Each prisoner is allowed to open 50 boxes, and if each prisoner gets their number, then they all go free. However, if one prisoner gets one wrong, then they all die. If they all go in and choose at random, then each prisoner has a 50% chance that they will find their number, and if they all do that, then their odds are about 1/2 to the power of 100, which is such an astronomically low probability that they're pretty much doomed to fail. However, there is a strategy that raises their odds all the way up to 30%, and this strategy goes as follows. Each prisoner will go in and open the box with their number, and then if that box does not have their number in it, they will go to the box that has the number that was in the other box and go open that one. Each prisoner will do this until they eventually find their number, as all numbers should technically lead back to each other on a loop. The only problem with this is that if any of the loops are bigger than 50 numbers, then they're all doomed to die. However, if the largest loop is less than 50 numbers, meaning 49 boxes, then they will all go free, because if they use this, they will all find their number. So the next entry is the Sleeping Beauty Paradox, and this one is not named after the movie, but it's a paradox in probability that states, suppose Sleeping Beauty undergoes an experiment where she is put to sleep using an amnesia that is powerful enough to make her forget she was awake, and a coin is flipped on Sunday. If heads, then she will be awakened on Monday and interviewed, but if tails, then she will be awakened on Monday and Tuesday and interviewed. Again, this amnesia is strong enough to make her forget waking up, so she is finally awakened on Wednesday and asked what she thinks the probability of the coin landing on heads was. The first solution you probably thought of was that it's 50-50, which is plain and obvious, a coin can only land on heads or tails. But however, there is a second solution that believes that the probability is actually 1/3, because there are 3 possible awakenings. There's heads on Monday, tails on Monday, and tails on Tuesday. So again, neither of these are wrong or right. So the next entry is Kramer's paradox, and in this one, imagine you have 2 complicated curves and you want to know where they intersect. Paradox here is that the number of intersections might be more than you'd expect, making it seem like you have enough information to figure out each curve uniquely. The reason for this is because one math rule states that the number of intersections depends on how wiggly a curve is, and another rule states that you need a certain number of points to uniquely identify each curve. So in certain cases, you'll have more points than you actually need, and it turns out that these points don't help you uniquely figure out each curve at all. So the next one is Richard's Paradox, and I'm not going to spend like any time on this one as it's practically Barry's Paradox, but in like much more complicated terms. So this one basically takes what Barry's Paradox is and adds regular English phrases to it instead of just numbers. So it just makes it a whole lot more complicated, and you know, it's practically the same. So there's not really much you can add to it. If you don't know what Barry's Paradox is, go watch the last video, and it's about a third of the way into tier 4. So the next is Ernfrest Paradox. Forgive me if I butchered that, but this is another confusing one with numbers that I don't really understand, but I'm going to try my best. Imagine a rigid disk rotating at constant speed. The paradox is what happens when you measure the disk when it's spinning and when it's at rest. According to relativity, things in motion should appear contracted due to a phenomenon called the Lorentz contraction. However, when you measure the disk when it's both spinning and resting, the radius actually remains unchanged, and so the measurement are now the same, which according to Euclidean geometry, it should not be. So the next is the ladder paradox, and for this one, imagine that you have a ladder whose length is too long to fit inside of a garage. This garage has a door on each side, so you are able to push the ladder through the garage. If you move the ladder at a very high speed, it undergoes length contraction, which I talked about in the last one, and therefore it should be able to fit inside the garage at some point if it's going fast enough. So say hypothetically it is doing this, and you close the garage doors just before you can reach the ladder through the last one, and now you have a ladder whose length is longer than the garage inside the garage. So the ladder should not fit, but now you're in a situation in which it does. So the next one is Kepler's Dream, which is a book by Johannes Kepler, where people imagine being on another planet observing the sky. So in this dream, these people might see planets moving in different ways, and Kepler used this imaginary scenario to show that the laws governing planetary motion, which he later described in his Kepler's laws, could apply universally and not just to Earth. Basically, this theory helped him to understand how planets move around the sun. So the next one is a philosophical zombie, and this is a being that looks and behaves exactly like a human, but lacks consciousness or subjective experience. This is a way for philosophers to explore the idea that someone could outwardly act like a conscious person without actually having any inner thoughts or feelings. This concept helps philosophers to discuss the nature of human consciousness and what it actually means to experience something. The next is the Renninger negative result experiment, which is an experiment in quantum mechanics that deals with the study of wave function collapse. So this experiment is involving a radioactive atom about to decay, and it emits an alpha ray. Instead of a cloud chamber, Renninger envisions two hemispherical particle detectors surrounding the radioactive atom. If one detector registers the decay, then the other won't, as a single particle cannot be detected by both simultaneously. The paradox lies in the non-detection on one hemisphere, implying a partial collapse of the wave function to a singular hemispherical shape. This would occur before even interacting with the other hemisphere, leading to the conundrum that wave function collapse can occur without actual particle detection. So the next is the Elitzer-Weidmann bomb tester. Again, forgive me if I butchered that, but this is a quantum bomb that can either be exploded or be safe. So traditional thinking suggests that the bomb state could set it off. So again, this is much like quantum immortality and Schrodinger's cat that I mentioned in the other tiers, where you have something that happens at both times, even though it can't. So in this, imagine you have a bomb that you send photons into, which allows photons to take both paths simultaneously that would either set it off or not. Again, this is a very odd situation in which you have a bomb that is alive and not alive at the same time. Again, this illustrates how weird quantum mechanics is, because you have a bomb that is both alive and safe at the same time. And that, quantum mechanics is a very weird concept. So the next is Argumentum Ornithologicum, which is a thought experiment debating the existence of God. This one was kind of hard to find, but what I think it is goes as follows. I close my eyes and see a flock of birds. The vision lasts merely a second, and I don't know how many birds I saw. Was there a definite or indefinite number? This problem involves the question of the existence of God. If God exists, then the number is definite. because how many birds I saw is known to God. However, if God does not exist, the number is indefinite because nobody was able to count it. So let's say in this case, I saw fewer than 10 birds and more than 1. But I did not see 9, 8, 7, 6, 5, 4, 3, or 2 birds. I saw a number between 10 and 1, but not any of those numbers I just mentioned. That number, as a whole number, is inconceivable, therefore God exists. So, the very last entry on this iceberg, I see it as very fitting that this entry comes from the kids' book series, Captain Underpants. Again, I find this very ironic considering that half of this list was quantum mechanics or physics or math, and the last one is a time travel paradox that comes from a kid's book. Anyways, in this, a scientist in 2020 makes a banana pie from his own tree and goes back in time to 1963, where he accidentally goes to a restaurant and smashes it on a woman's face. This then starts a pie fight in the restaurant and causes chaos, and someone trips over the original banana tree, causing the timeline of the story to become in shambles until someone goes back and fixes it. While yes, it's stupid, it does show the rippling effects of time travel and how something small in the past can have drastic effects on our future. And one little rock throw in the past, 2,000 years ago, if you altered that, you couldn't alter the course of human history. I don't know. I just find it interesting, and I think it's a funny way to end this tier list. Anyways, y'all, I hope you enjoyed this last part of the iceberg, and I'd love to know what y'all think about it in the comments. You guys might have noticed the change in scenery in the background and me holding the mic and, not having it on an arm. But this is because I moved back to college, and so because of that, I'm going to try to get on a schedule and have videos hopefully uploaded twice a week, once on Wednesday, once on Friday or Saturday. Haven't really decided. I'm going to try to get on a schedule because I got classes and all that stuff going on, so it might take me a month to fully work everything out, but I'll get there eventually, and I'm going to, try to stick to consistent posting. Anyways, y'all, this video did take quite a while to make. So as always, it would mean a lot to me if y'all subscribed, and commented. But anyways, I'm mindful, and I hope to see y'all in the next video.